Good afternoon, morning, evening, whenever. Made this video for you all to have quiz prep for quiz 10, which is going to be focused on validity of arguments. This is because only the Monday sections are meeting for week 15, so I just want to make sure that we have everything we need for our last quiz. So first, we have this Euler diagram in front of us. And what we need to do is select the statement that best describes the relationship that we've depicted here. So if you want to go through each statement exhaustively, you can do that. But right out of the gate, since I see that there's an intersection between cats and animals that sit, I can already infer that we're looking at some cats that sit. Now, from here, a little bit of process of elimination will do you well. Obviously, all cats don't sit because there are some cats that are in the space of cats that don't intersect with the space of animals that sit. Obviously, there can't be no cats sit because there's somebody in there, or some cat rather. Okay. Then we have to be careful about the conditionals. Okay, if it is a cat, then it can sit. That implies that if I choose something in the cat universe, it has to also be in the animals that sit universe, which we know is not the case. Okay, if it cannot sit, let's consider this statement here. If it cannot sit, then it is not a cat. So let's put something in the universe of things that can't sit. Right, so I can put something out here. Does that necessarily mean that it's not a cat? Well, in this case, that's true. But what if I put my animal here? Well, it's outside of the universe of things that sit, but it's within the cat universe. So C is not going to work. And by the same argument, A will eliminate itself because if we have a cat, that doesn't mean that it has to not be able to sit. Okay, we could have something in the intersection. All right. Now let's consider cows, animals that run. Actually, let me go ahead and do horses and animals that run. I don't want to do all of the problems, otherwise this video is going to be really, really long. But some of these are very similar. So, okay, right out of the gate, we see that horses and animals that run, these are disjointed sets. When sets are disjointed, what that means is that they have no intersection. Therefore, we can go so far as to say there are no horses that run. Okay, there's nothing that they have in common. All right. Now, from here, some horses run, definitely not the case. Now, let's consider B. If it is not a horse, then it can run. Well, I mean, I can definitely, so I need to go outside of the horse universe. All right, I'll put my animal here. Well, it's not a horse, but it can't run. So B is not going to work. If it cannot run, then it is not a horse. Okay, so let me go outside of the universe of animals that can run. All right, certainly in this case, it's not a horse, but I could also land here. I mean, I'm an animal that can't run, but now I'm a horse. So that is not going to work. If it is a horse, then it cannot run. So let's put something in the horse universe. Is there a way I can put something in the horse universe that will make it able to run? Nope. So if it is a horse, then it cannot run. That works. And obviously all horses can't run because none of them can. Make sure you take your time on these types of statements, okay? It's really easy to make some just goofy errors, right? So really make sure that you slow yourself down and consider all of your options. All right, now here what we're doing is we're effectively practicing the construction of our own Euler diagrams in a few particular cases, and then some of them we don't need to actually construct Euler diagrams. So ultimately, whichever, however you think about this is a completely fine way to view it. I'm going to go ahead and do problems 1 and 3 from here, because those are the ones that students tend to get the most hung up on. So let's start with all shrimp are appetizing. So I'm going to start with my universe of things that are appetizing. And now I'm saying that all of the shrimp live in here. Now, all shrimp are appetizing, so I can't have a situation where there's some shrimp that pop out of the appetizing universe. They have to be properly contained. Now, which, by the way, if you don't think shrimp are appetizing, that's fine. You're just mistaken, and that's okay. We forgive you. And now we have that tiger is a shrimp. All right, so here's where tiger lives. So tiger is somewhere in that S universe. So now we consider, does that mean that tiger is not appetizing? Well, certainly not, because tiger is still in our orange universe, or I'm sorry, purple universe. Therefore, tiger is appetizing. Yep, that's forced to be true. Therefore, all shrimp are named tiger. That's not true. There's all kinds of little shrimpies that aren't tiger. Therefore, some shrimp are not appetizing. Well, that's impossible, because then our shrimp universe would have jumped out here, which it couldn't. All right. Now let's look at number 3. Now, this is going to be a little bit of a point of contention. Some folks call it pecan pie. Some folks call it pecan pie. It doesn't matter. It's garbage. And again, if you like pecan pie or pecan pie or whatever, it's fine. You're just mistaken. And that's okay. Again, we forgive you. No New Yorker likes pecan pie. All right, so we've got the space of New Yorkers. And we've got the space of pecan pie lovers. Okay. Now, we would say all Southerners like pecan pie. So all of the Southerners got to be contained into the pecan pie universe. I can't have the Southerners explode, any Southerners explode out of there, because if they do, then that implies that there are some Southerners that don't like pecan pie. But all Southerners like pecan pie, whatever. Now, we're going to analyze the relationship here between Southerners and New Yorkers. Therefore, all Southerners are New Yorkers? Well, no. Anything that's a Southerner is definitely not going to be a New Yorker, because those are mutually exclusive sets. Definitely not that. Those are disjointed sets. Therefore, no New Yorkers are Southerners. Well, yeah, that's true. If I choose any New Yorker, there's no way it's going to pop into the space of Southerner. That's impossible. These are disjointed things. Therefore, all New Yorkers are Southerners. Certainly, if Southerners can't be New Yorkers. If they're disjointed sets, then obviously all New Yorkers can't be Southerners. Some New Yorkers are Southerners. Well, no, they're disjointed, so they don't have anything in common. Some Southerners are New Yorkers. Nope, they're disjointed. Therefore, no pecan pies are made in New York. We can't actually, so this is a tricky one. We can't actually make that inference. We had nothing in there about where pies can be made or anything to that effect. Now, certainly, we can agree that if no New Yorker likes pecan pie, which it appears that that's the situation we're in here, it wouldn't be a great idea to open up a pecan pie shop in there, but that is not an inference that follows directly from our premises stated in the argument. And so this is where students make the most mistakes in this section, is they will have a penchant for kind of extending their argument a little bit too far. Okay, and we've seen that happen in news and debate and media. We see it all over the place. Folks who tend to take one small fact and blow it up a little bit farther than it needs to go. Now, it always snows when it's cold. I like using Euler diagrams for quantified statements. So I'm going to say cold. Whoa, I'm going to write cold like I have some notion of motor skill. Okay, so we've got cold, and it always snows when it's cold. Okay, so in the space of cold, you would say, okay, snow. You could actually even say that these things are kind of the same. Every time it snows, it's cold. Okay, it's snowing, therefore it is cold. This argument is absolutely valid. Okay. Ultimately, as long as there's something in the snow universe, it has to be properly contained in the cold universe. Okay. Now, just because it's cold, does that mean it has to be snowing? Well, now that's a different thing altogether. We have that it's snowing, so there you go. Now, let's take a look at the second one. I want to do that one. So we've got some birds can fly. Right, so some birds cannot fly. All right, so we start with some birds. Got birds. And then we'll say fly. Got birds. Now we're saying some birds cannot fly. So there's going to be an intersection, which is fine. And now we're going to say all birds have feathers. So we'll say fly. And then I'll draw a little feather here. Boop, boop, boop. That's a feather. Not a chicken drumstick. That is a feather. So there you go. Now we're saying all birds have feathers. So got to draw a drumstick, whatever. Let's make that look a little bit more convincingly like a feather. That's, that's as good as that's going to get. So we have to contain all of the birds, okay, because all birds have feathers. Now, therefore, some things that don't fly have feathers. All right, so let's consider this. Some things that don't fly. So what we want is some intersection between the things that don't fly and ultimately what that's going to be is everything else in my universe. Some things that don't fly have feathers. And is that going to intersect with my red space? So what you can do here is let me consider my universe. This is the universe, this is everything, right? If I draw this diagram in here, so here's my birds, here's my feathers. I'm trying to make it not look like a drumstick. And then here's my fly. We'll have just a little bit of intersection here. Now, here's the thing I want us to think about. Here is the complement of fly. And so what I want to know is there some intersection between this space and feathers? Well, with a little bit of inspection here, I can actually even get rid of fly at this point. If I consider the complement to be everything that was not in fly, then we see that it does flop a little bit in here. So this statement, this argument, as weird as it is completely valid. Okay. Ultimately, in the not fly, there is some of the not fly that falls into the feather category. So we have things that don't fly that have feathers. That one's really tricky. In my opinion, that might be one of the hardest ones on this particular homework assignment. All right. So let's take a look at Bill. for this one, recommend that you use propositional logic, and I would even use a symbolic representation. So Bill will go to the movies, we'll call that P. Or Sam will play golf, we'll call that Q. And since we said or, that's a disjunction, boom, you have that. And now what we're saying is Sam does not play golf. Okay. Now what we want to know, therefore, is what can we infer from this? Well, we're going to use the law of disjunctive syllogism. Disjunctive syllogism. It's really important you know this vocabulary. By the law of disjunctive syllogism, we have P. If P or Q, and I have that not Q, then I have P. So therefore, Bill will go to the movies. Now, some of you may be thinking to yourself, where did that actually come from? Vocabulary, 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 vocabulary. Make sure you know your vocabulary. Okay. Now, what I'll just go ahead and do is just run through these next few just so that you have it available to you. But I will take a look at the third one here. All right, now for number 2, I'll leave the particular details to you. You can take a look at this in the actual notes. But you're going to use the law of syllogism here. All right, you're going to use the law of syllogism, and you're going to get E. If you pass the exam, you can sell your book. Now for number 3, what we have here is, if it snows, then the ball game will be rescheduled. All right, so we'll say if P, then Q. My other premise, I'm saying the ball game is not rescheduled. Okay, so that's not Q. What law am I using here? The law of contraposition. So what we have is not P. It did not snow. Okay. For number 4, you're going to want to use an Euler diagram for that, since it's a quantified statement. All right. Try not to use you're not going to find any vocabulary that's going to work for that one nicely. You'll need to do an Euler diagram for that because it is quantified statement. So make sure that you're minding that. All right. Now for number 7, this is using all of your knowledge about Euler diagrams. And again, what we're trying to do is find intersections, possible intersections between 2 statements. So I'll leave that. I'll do one so that we have some kind of example. Let's do men and giraffes. Some men are tall. All right, so here's my men. Some of them are tall. So there's an intersection. Must be nice to be a tall man. I don't know. It's not for me to know. Some giraffes are also tall. Fun. So we could have giraffes do this. Some of them are tall. I don't know. Not all of them. Now, the statement we're going to say is, therefore, some men are giraffes. Well, okay. So in this Euler diagram, it's pretty clear that I can make one where men aren't giraffes. Now, I also could make one like this, right? Then there are some men who are giraffes. But because it's possible for me to do this, that means that I cannot sufficiently say that there are some men who are forced into being giraffes or giraffes who are forced into being men. I can make those universes mutually exclusive. I can make them not intersect. Okay. So this is an invalid argument. It really doesn't take much work to make an Euler diagram invalid. It really doesn't take much work. All right. Let's do black and white and zebra. All right, so here are my animals. And some of my animals are black and white. Just some of them, not all of them. This zebra, just this one, is black and white. There we go. Therefore, this zebra is an animal. Well, no, it doesn't have to live in here. So this is actually an invalid argument. Okay. And I'll leave you to take a look at the problems from 9. You'll see that these are very similar to the problems from 8. For 10, let's talk about Kathy. We have that Kathy is a poet or a cheerleader. Let's use symbolic logic. Let's say Kathy is a poet, we'll call that P. Kathy is a cheerleader, we'll call that Q. We have or, this is a disjunction. So Kathy is not a cheerleader. All right. That's cool, Kathy. You do you, and you decide to not be a cheerleader. That's fine. Therefore, Kelly is a poet. Wait a second. So here's the thing. Or wait a minute. Blip. I'm not going to do this whole thing over. Oh my gosh, that is so much work. So I used, I said some words wrong. Kelly is a poet. So that's P. Kathy is a cheerleader. That's Q. Kathy is not a cheerleader. So we're talking about Kelly and Kathy. They're separate people. So is Kelly a poet? Yes. This is the law of disjunctive syllogism. Now, believe it or not, if Kathy was a cheerleader, if we said that Q, if we said P or Q, if Kathy is a cheerleader, that does not mean that Kelly could not be a poet. Some folks would say, oh, well, then Kelly can't be a poet if Kathy is a cheerleader. That's not true. That's actually the fallacy of what's called the inclusive or. In an or statement, in a disjunctive statement, it is possible that both of them are true at the same time. But if one of them is false, the other one has to be true. So this argument is valid. Right. If my genes are too tight, then I will go on a diet. Oh, this hits close to home. So, okay. If my genes are tight, I will go on a diet. We'll say P is my genes are tight. Q is I'll go on a diet. I'm given that P, my genes are tight. What naturally follows from here by the law of detachment. Does it help to know all this vocabulary? Yes. I have that Q necessarily follows. Okay. So therefore, I will go on a diet. This is a valid argument. While boring, valid. All right. Now, for 18, we have a maple tree. If you have a maple tree, so we'll call this P, then you have to rake leaves in autumn. This is Q. So we have if P, then Q. All right. My next premise, John has to rake leaves in autumn. So we have Q. Now from here, we're saying conclusion, John has a maple tree. Therefore, we're saying P. This is an invalid argument. This is what we call the fallacy of the converse. Now, here's where folks will make a mistake. They'll say, oh, well, no, there's all kinds of other trees, blah, blah, blah. They start talking about, I don't know, horticulture in some form or variety. Look, we don't need all of that. We don't need all of that horticulture. The fact of the matter is that this is the fallacy of the converse. It has nothing to do with trees or leaves or any of that nonsense. The fact of the matter is we have a fallacy of the converse. So the argument in and of itself, is invalid, and we don't need any information about trees or leaves or any of that nonsense in order to discern that the argument is invalid. Okay. Now, let me take a look at 21, and then we'll take a look at 22. Okay. This one tends to confuse folks just because they see the word triangles and they get sad because geometry is a bummer. If a figure is a triangle, we'll call that P. The angles add up to 180 degrees. We'll call that Q. All right, so we've got if P, then Q. The figure has 3 sides. Ooh, we're introducing something new. We'll call that R. Then it is a triangle. Oh, that's P. Then we have if R, then P. That's cool. So, therefore, if a figure has 3 sides, all right, that is R. Then the angles add up to 100 degrees, Q. Is this true? Well, all right, let's start at R. We have in our second premise. Go from R to P, and then from P to Q. Yes, we can go straight from R to Q. This is called the law of syllogism. It's a weird one because it's not the way that we would normally order the statement. We would normally try to start it with like, if R then P, and if P then Q. Most folks would switch the ordering of that, but it doesn't matter what order we say it in. True is true is true is true. And even outside of truth, it's a valid argument. So even if I wanted to say something crazy, like a figure is a triangle, then the angles add up to 179 degrees, we know that's not true because, you know, the interior sum of angles, if triangle add up to 180 degrees, blah, 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 blah. But if everywhere I saw 180, I put a 179 in this place, that wouldn't mean that the argument would be invalid. Actually, by the law of syllogism, the argument would be perfectly valid. The problem is it wouldn't be true. The argument wouldn't be true. Now, you can have valid arguments that are false, and you can have invalid arguments that are true. They are different things. Valid and invalid has everything to do with consistency and not necessarily true. We can say things that are valid that are patently false. It doesn't take too much work to think of somebody who might share a particularly different worldview than you to say something that might be valid and might actually coincide with their particular sense of worldview, but might be false. And vice versa. We might find someone who we agree with who actually have invalid arguments to support their claims. These things are mutually exclusive, which is shocking. Now, that being said, let's take a look at number 22. If a child is 8 years old, call that P, then they attend school, Q. If a child attends school, that's Q, then they play at recess, we'll call that R. Therefore, we're saying if a child is playing at recess, okay, so, or no, I'm sorry, we said R. Then she is 8 years old. R then P. Well, here's R, but I can't go backwards unless I use the fallacy of the converse. So this is an invalid argument. And what this is the improper use of syllogism. Now, again, try not to think about 8-year-olds and recess and all that jazz. Think of this as just a symbolic representation of a logical statement. Okay, from the just formulation of this argument, regardless of what we know about children and 8 years old and recess and school and all that jazz, we don't need any of that. The fact of the matter is that this argument is invalid. All right, good luck on your quiz.